We're jumping straight into the paper. Benchmarking on-device machine learning on Apple Silicon with MLX. This analysis is for any engineer wondering if their next laptop can finally replace that cloud compute bill.
And we've pulled out the three most critical insights from this research, the ones that really shift how we think about on-device AI.
Okay, first up, the performance hierarchy. It's still what you'd expect. Specialized hardware leads the pack.
Right. The NVIDIA A10 SITA GPU using PyTorch is still the undisputed champion for raw speed. That dedicated data center advantage is, it's very real.
But, and this is the real story, insight number 2 is how fast Apple Silicon is catching up. The jump from the M1 to the M2 Max is just enormous.
It really is. I mean, for BERT-based inference, the old M1 was way behind at around 179 milliseconds. The M2 Max just crushes that, getting down to 38 milliseconds.
Which is shockingly close to the CDA GPU's 23 milliseconds.
Exactly. That's a massive gap closure in just one generation.
And that brings us to the third finding, which is a huge win for optimization. Highly efficient parallel processing. The M2 Max showed this amazing sublinear scaling on batch tasks.
This is the part that should really get technical folks excited. They ramped up the batch size by 32 times, a huge workload increase, and the inference latency only went up by about 9 times.
That is some serious scalability for a consumer device.
It is. So today, our mission is to break down the MLX framework, figure out how Apple's unified memory model makes this possible, and really dig into the data to see what this means for your workflow.
There's a big push for on-device machine learning right now.
It's really a matter of necessity. It comes down to adoption and scale. We're seeing LLMs and other big models being used everywhere.
And these models are. They're huge.
Yeah.
Billions of parameters that used to be stuck in the cloud.
Exactly. And most developers can't afford a data center GPU in their office, so there's been this huge effort to get these models running locally.
Which has led to all these model compression techniques, right? Like quantization.
Precisely. That's the most common one.
For anyone listening who isn't deep in model compression, can you give us the quick 1 minute on what quantization is?
Absolutely. So in simple terms, quantization is just reducing the numerical precision of the model. Think of it like this. Most models run on 32-bit floating point numbers.
Okay.
Quantization can drop that down to 8-bit or even 4-bit integers. It makes the model file dramatically smaller so it fits on your device, usually with just a tiny hit to accuracy.
So you've got these smaller models, and now you need the hardware and software to run them fast. And that's where Apple's strategy with its own silicon and the MLX framework comes in.
Correct. MLX was built from the ground up to take advantage of the M-series chips. It's an optimized environment that just makes research and prototyping so much easier on a Mac.
And the key architectural feature it leverages is the Unified Memory Model, the UMM. This is the real game changer compared to a traditional PC with an NVIDIA card, isn't it?
It's the defining feature, really. In a standard setup, you have your system RAM for the CPU and then separate dedicated VRAM for the GPU.
And moving data between them is slow.
It creates bottlenecks, latency, you have to duplicate data. It's a mess for large ML workloads.
Right.
UMM gets rid of all of that. The CPU and the GPU share one big pool of high-speed memory. They can both access anything instantly. No more copying data back and forth.
So that's the core advantage MLX is built on.
It is. And to make it easy for developers, the paper talks about MLX-Transformers.
What does that library do?
It basically just simplifies everything. You can grab popular models like BERT, Llama, whatever, straight from Hugging Face and run them natively in MLX.
So no more headaches with converting model checkpoints or building weird compatibility layers?
None of that. It's designed to just work, which is a huge barrier removed for researchers coming from a PyTorch world.
Okay, so to actually measure all this, the researchers had a pretty rigorous setup. Let's talk about the hardware they tested on.
Yep, they had 3 main devices. So on the consumer end, an 8-gig Apple M1 MacBook Pro, and then the much beefier 32-gig M2 Max MacBook Pro.
And for the industry benchmark,
An NVIDIA A10 GPU, the CUDA-enabled one, running on an AWS cloud instance, your typical enterprise-grade workhorse.
And the tests were broken into 2 main parts.
Right. First was operations benchmarking. They looked at the fundamental building blocks, matrix multiplication, and so on. They compared MLX on the Apple chips against PyTorch on the A10.
And the second part?
Model inference benchmarking. This is the real-world test, running actual models like BERT and RoBERTa and timing them.
And they varied the workload to simulate different scenarios, too.
They did, which is crucial. They tested different input lengths from 50 up to 500 characters, and also different batch sizes, 1, 16, and 32, to check the parallel processing chops.
All right, let's get into the results. Starting at the lowest level, the individual operations. The A10 is faster, no surprise, but by how much?
Yeah, the A10 was consistently dominant here, but what the M1 could do is still really impressive for a consumer chip that's also trying to save battery life.
So let's look at the operations that are staples for transformers. Matrix multiplication, linear transformations, and softmax. What were the numbers?
Okay, so for matrix multiplication, or matmul, the A10 clocked in at a blazing fast 3.96 milliseconds. The M1 GPU took about 26.19 milliseconds.
Still pretty fast, but a noticeable gap. What about linear?
Even closer there, 3.11 milliseconds on the A10 versus 18.8 on the M1. But the big one was softmax. Yeah, here the A10 was just 1.06 milliseconds. The M1 was way back at 27.91 milliseconds.
Wow, the huge difference, almost 27 times slower.
Yeah.
Is that a weakness in the architecture, or is that just MLX not being as mature as PyTorch and CEDA yet?
That's a great question. I'd lean towards optimization maturity. I mean, matmul and linear ops are what GPUs have been optimized for decades. They're the bulk of the work.
Right.
Softmax is a bit more nuanced and involves different data movements. MLX is the new kid on the block, so it makes sense that they're still playing catch-up on optimizing those more specific operations compared to PyTorch.
Okay, that makes sense. So now let's go from those building blocks to the main event. Overall model inference. This is where the M2 Max really flips the script.
Absolutely. The performance leap from the M1 to the M2 Max is it's staggering. Again, the A10 is still the fastest overall, but the M2 Max makes it a real contest.
Let's use BERT base as the example.
Yeah.
What were the average inference times?
So the A10 CEDA GPU averaged 23.46 milliseconds. The M1, a very slow 179.35 milliseconds.
And the M2 Max?
A fantastic 38.23 milliseconds.
Whoa! So that's almost a 5x speed up in one generation. That takes Apple Silicon from being a curiosity for ML to being a genuinely viable platform.
It really does. And the same thing holds true for the much larger BERT large model. The A10 was at 62 milliseconds, the M1 was over half a second, and the M2 Max came in at 94 milliseconds.
So the gap is consistently narrowing. But we have to be fair here. The hardware wasn't exactly an apples-to-apples comparison, right? The M2 Max had way more memory.
That's a very important point of skepticism, yes. The M2 Max they tested had 32 gigs of unified memory compared to just 8 gigs in the M1.
So is this really a win for the M2 chip's architecture, or are we just seeing what happens when you throw more memory at the problem?
It's both. But the memory is a huge factor, especially because of the unified memory model. With 32 gigs, the M2 Max just isn't memory bound in the same way. It can hold bigger models, bigger batches, without needing to swap.
So it's demonstrating that to really unlock the potential of MLX, you need to max out that unified memory.
I think that's the key takeaway, yes.
Okay, but even then, for an enterprise user looking at these numbers, 94 milliseconds on the M2 Max versus 62 on the A10, the A10 still has other advantages besides just latency.
Oh, absolutely. The A10 is a data center workhorse. It's built for throughput, how many requests it can handle at once. It has better thermals, better power efficiency at scale. You buy an A10 for production. You buy an M2 Max for incredible local development.
Now, for the part that I think is really fascinating, for any developer trying to optimize their models, how performance scales. Let's start with input length.
Right, this is so important. They looked at the M2 Max data going from 50 up to 500 characters. For BERT base, the increase was pretty linear. It went from about 17 milliseconds up to 76. Predictable.
But RoBERTa base was a different story.
A very different story. It started off faster than BERT at just 11 milliseconds for 50 characters. But at 500 characters, it jumped all the way to 201 milliseconds.
That's a huge nonlinear increase. For an engineer, that's a massive red flag, isn't it?
It is. If your app uses RoBERTa and you expect long user inputs, you have to account for that aggressive latency spike. It might even mean you can't use RoBERTa at all if you have a real-time requirement.
It could force you back to a model like BERT-based that scales more predictably. That's a really practical insight.
It's the kind of thing you only find out by benchmarking like this.
Okay, now let's get back to that third critical insight from the intro, the sublinear scaling with batch size.
This might be the most powerful finding in the whole paper. They saw that as they increased the batch size from 1 to 16 to 32, the performance got more efficient.
Right. The scaling was sublinear. Can you break down that specific BERT-based example again?
Sure. So on the M2 Max, a single inference, batch size of 1, took 8.02 milliseconds. A batch of 32 took 70.48 milliseconds.
If it were linear, you'd expect 32 times 8, so over 250 milliseconds.
Exactly. Instead, you get a 32x increase in work for only about a 9x increase in time.
So how does the unified memory model physically enable that? What is the M2 Max avoiding that a traditional VRAM system gets stuck on?
It's all about avoiding data movement. In a traditional system, with every item you add to the batch, you're adding more data that has to be copied and coordinated between the CPU and GPU.
That transfer overhead becomes the bottleneck.
Right. It starts to dominate the actual computation time. Because UMM completely removes that copy step, the M2 Max's GPU cores can just stay busy doing useful work. That's how you get that incredible sublinear scaling. It's a fundamental win for batch processing.
So putting it all together, the big picture is that MLX on Apple Silicon is now a genuinely compelling platform for on-device inference and local development.
That's the core message for developers. For research, for prototyping, for certain low-latency applications, this is a huge step forward. It really helps democratize access to this kind of power.
And the practical advantage for you, the developer listening, comes down to cost.
It's huge. You can run all these experiments on your laptop without racking up a massive cloud GPU bill. It makes MLX on Apple Silicon a really viable alternative.
We do need to add the caveat, though. This isn't replacing the data center just yet.
No, not for full-scale production workloads that need massive throughput and 2047 uptime. That's still cloud territory for now, mostly because of thermals and scale.
But the paper is really optimistic. That M2 Max performance jump and the batch scaling, it suggests we're getting much closer to a future where more complex models run efficiently right on our desks.
The researchers even suggest future work should look at not just bigger inference, but on-device training of smaller models.
And that changes the whole paradigm. If you can train and infer locally, your reliance on the cloud just shrinks dramatically for a huge number of use cases. This research suggests that ML tasks currently locked behind expensive cloud GPU access could move to your local machine very soon. So the question this leaves for you is, which of your tasks, fine-tuning, batch processing, or RAG, will you be moving to local execution next year, making the democratization of AI a reality right there on your own desk?